Log on, tune in, find out. Another good idea from Cambridge.
Derek, it's all yours.
Let's go right to the end. All right, so I'd like to thank Shane for inviting me to talk today. All right, so it's interesting. So today was going to be a day where there's a lot more talks geared towards applications and where people can think about this. This is the overall theme here for the program here at the Newton Institute. There's been like 5 workshops related to design of experiments in different places where design rears its ugly head. And this is one particular one, but we wanted to have some application talks. And so when Shane works on a lot of these things and does some really good work, so I encourage you to look up his work. And so I thought, okay, well, how am I going to, when he couldn't make it and he's sick, so we thought, well, we'll throw in an application talk. And Tom Angela said, Derek, you work in some applications here, so why don't, do you mind doing that? And I said, sure, not thinking about what talks I actually had on my laptop. So I go to my laptop and notice I have none. And so at the bottom of my bag was a memory stick. And so I pulled out and said, oh, there's got to be something on it. And thank God there was something on it. Otherwise, I'd just be telling more stories about Shane, and it probably wouldn't be good. Anyway, Shane, if you view this talk, there are no more stories about you. Anyway, all right, so I'm going to talk about something called, I'm going to do a calibration problem here. So this is, so we've heard a lot about model calibration. What you're going to see today is a calibration, but probably more likely you'd think of this as a tuning exercise for something called radiative shock physics, which I'll talk about in a second. And in this particular case, this particular group is investing a lot of time into what I think broadly can be called predictive science. So they are building computer codes that try to, where they would like to be able to use these things to use the codes and some physical observations to be able to make predictions. And I will say that the big problem out there is that we're not there yet, but is to learn enough about the physics, get enough information through codes, get enough experiments where they're able to start saying something about what they can do in unsampled regions. So extrapolation is going to be a big deal in the future, certainly for this group, and I know that's certainly is true for the climate folks as well. So this work is with myself and a graduate student and two of the physicists at the University of Michigan. So let's just dive right in. So what is radiative shock? So this is done, the work here is done through the Center for Radiative Shock and Hydrodynamics at the University of Michigan. So radiative shock is a shock wave. So there's an explosion, causes a shock wave, and the shock wave has this energy density that is so high that the energy balance requires that radiation radiates away from the shock wave. And so what you really do is you get radiation coming out in front of the shock, and so you end up with kind of think of it as 2 different shocks kind of going on, this radiative shock and followed by the initial blast, if you will. And the physics here is relevant to astrophysics and supernova, solar winds, solar weather, that sort of stuff. So this is where the interests lie. And certainly you get radiative shocks wreak havoc, for instance, with satellites and communication systems and things like that. So at the, they have the ability to actually do experiments to create a radiative shock. And this is not easy. You need a really high-powered laser, and these things are very expensive to get time on, and we get enough to do about 8 to 10 runs a year. And this is a 5-year project, so they're able to do some runs every year, and the experiments change from time to time. But the idea is conceptually simple, is that there's a laser, there's a beryllium disk, and there's a tube. So the laser hits the beryllium disk, causes an explosion, a shock wave moves down this tube. Okay, so this is what you have. Now the tube, think, wow, there's a laser, there's a beryllium disk. We're talking things that are nanometers, and when you see the tube, it's very disappointing. Like I imagine this massive tube, and you're like, it's actually kind of this long. And all right. So one of the things that plays a part here is you get hydrodynamics. So think of that as kind of the movement of liquids and shocks through liquids and fluids and things like that. But you also get radiation at play here. So you get two different types of physics going on at the same time. So yeah, so this is it. The laser radiates the beryllium disk. You get so what's also interesting here is that the tube just does, the shock itself does not just move down the tube. That'd be nice, but it turns out that it actually interacts with the wall of the tube, and this is because of the heat and the radiation. The fact is that you get an ablation and stuff starts happening. So it gets a bit more complicated, and thus the physics that they build needs to be a little bit more complicated. Let's see if I can find this. No, it's not going to work here. Is this going to work now? All right. So this is kind of the end of a shock, actually. So I had a movie here, but going from the Mac to PC is not working out for me right now. So this is kind of the end of the shock. But what we actually have going on here is that at some point, this and this were actually together. And right after the explosion, or the way the shock is created, these things start moving apart, and that's where you get the first one is the radiative shock. The thing at the end is actually just an artifact. That's a computational thing that we're working on. So this little guy way over here, right, that shouldn't be there. Just pretend it's not there. And this here is what's called a radiograph. And let me just say that this is output from a 2D code. Okay, so in other words, so this here itself could be folded across here, and that would give you the shock. So you've got a cross section. The 2D code essentially gives you a movie. If you wanted, we're also going to have something called a 1D code, but what that would really be is, so one of the ways you can create a 3D code out of your 2D is just rotate it around the axis, and you say, oh, it's 3D, but it doesn't really have the dynamics of a three-dimensional code. The way to do this with a 1D is you would just, all it really is something going, the shock just, its location, and what you would see here is just a constant blur, and that would be making a 2D out of a 1D, but it would be very boring. All right, so what are the goals? So the goal is to learn something about radiative shock and improve the computer codes, learn about the physics. I mean, there's some real stuff going on here. It's not just, well, we'd like to build an emulator or a predicted model. There's a lot of people involved in this, and there's a lot of different goals, but one of the things we'd like to do is improve the predictive accuracy by leveraging the codes that they have available to them and the experimental observations. And they would like to be able to, at the end of the day, demonstrate that they can predict within the experimental variability. So there are machines here that you can't improve on, right? Because you're not going to do better than your measurement system, but you'd like to be able to predict within that ballpark, at least that order of magnitude. The other thing they would like to do, so down here at the top, right at the top, you're looking down the tube, and you want to be able to change the diameters of these tubes, but ultimately they would like to change the shape of the tube. They'd like to be able to make predictions on an apparatus that they haven't actually done tests on. So what they would like to do is all the experiments are going to be done on these first two kind of those kind of regimes, but in the 5-year experiment they would like to have learned enough about the physics in order to predict for this oval tube. Now it sounds like a very easy thing. All you've done is squash the tube a little bit, but ultimately it's an extrapolation because they don't know exactly how the physics is going to work in a non-symmetrical or not radial symmetric regime. So that's the hope. That's the goal. We're back to the world of having deterministic computer codes. So these are deterministic. They hit enter and we wait a long time. This is the codes themselves run on supercomputers, so they're fairly computer intensive. And we're going to use the Gaussian process model to do this. So I don't think I really have to do too much about, I'm not going to argue too much about the Gaussian process stuff other than to say this is usually the argument for using them, the footballs that you get there. So what do I have? What are the data? So we have the data that I'm going to use for today's presentation. We've got 8 experiments. This is from the first year of the project, and they're experimental variables. These are knobs that you can dial. These are think of it from an experimental design. They've got laser energy and the xenon fill pressure. So this is the stuff that's going in the tube, the gas that's in the tube. And the response that we're going to look at is the shock breakout time. So that's where the shock suddenly, the radiative shock breaks away from the hydrodynamics. So we've also got a 1D code, as I said. So this is kind of propagating the whole thing, but it's not taking into account the interaction with the wall and that kind of stuff. And there are experiment variables here, and one of the things that is the beryllium thickness, so the thickness of the beryllium layer, and they wanted to be able to understand whether there's any sensitivity to this. And the reason is so there is no beryllium shop that you can go to. So you get these things specially manufactured, and they come within manufacturing specs, but they want to know if within the variation of manufacturing, whether the beryllium layer is really going to matter. Total laser energy, xenon fill pressure. So we got some. I made a mistake here. So total laser energy and laser energy are synonymous. So take them to be the same here. They're calibration parameters, or these are things that are in the code. We don't measure them or know about them in reality with the real data, and so I'm calling them calibration parameters. And the physicists, they got really great names here: electron flux limiter, laser energy scale factor. So let me tell you about the laser energy scale factor. So in a 1D code, what ends up happening is the shock goes down the tube. But there's no interaction because it's not, there's no 2D, there's no second dimension that it's looking at. So the amount of energy that's transferred from the laser to the shock is too much because the shock isn't being slowed down by the interaction with the wall. So the laser energy scale factor is a number you multiply the laser energy by so that you don't transfer as much energy. And it sounds fancy here, but it's like, let's just multiply everything by 0.6 and everything will be okay, right? And so we want to figure out what the right thing to do here is. But this is common in a lot of computer codes where there are numbers that are part of the code. They're there. And they're there to make the code look like something, look like data, look like another code, those sorts of things. But they don't really have a physical meaning. And sometimes it's just because it's a parameter in a PDE. But there isn't, real life isn't governed by that. So actually, the laser energy scale factor is one such thing. And that's the reason it does not exist in the 2D code. It doesn't have to do this because you're getting that interaction with the wall as part of the model. So you don't, so the calibration parameter in the 2D code, we've got the electron flux limiter, but there are some wall characteristics, which is the wall opacities. All right, so we've got that. There are three experiment variables for the 1D code. There are only two of them in the 2D code, and the reason is that was run at the same xenon fill pressure. Okay, so it's actually constant. So it's not that it's still there. It's still part of the modeling procedure. It's just that it was held constant for those ones. So one, we've got 1,024 simulations. So you can run the 1D code when you have computer time. You can run a lot of simulations here. And there's a reason why it's 1,024, because we gave them we was all based on a series of orthogonal array base Latin hypercube designs with a space filling criterion sitting on top of them. And the other ones was a similar sort of thing. Now, the reason there was 104 simulations is that we didn't know how many we would actually get, right? So they'd say, well, here's your computer budget, but you don't know when you're going to run out of budget. Right? And so we said, what we did was we actually took an 80-run space filling design, and we said, okay, and then we added batches of 10 conditional on each, so I had my 80 runs, and I said, okay, what's the best space filling design with 90 now, with those 80 already done? Because we thought we might run out of computer time at 80, and so we just kind of add 10 at a time and we eventually ran out at 104. As soon as you're at a computer budget, you're done, or you got to pay for more, right? So, and we didn't want to pay. So, all right, okay. So what's our setup here? So notice that the x's, if you will, the experimental variables are common across the simulators, at least insofar as they were fixed for the 2D code. One of them were, and the other two were adjusted. So we had three x's, if you will, three-dimensional input. The calibration parameters, well, we have calibration parameters are operating in reality, but there's one that's in common with both simulators, and one that only appears in the 2D code and one that only appears in the 1D code. So we have those guys. And so what we'd like to do, though, is put this all together and build a predictive model for the field. That's really the goal here. So we're going to try to get all this stuff together, noticing that the inputs aren't all the same. The 2D code the 2D code and the 1D code are thought to be, well, the 2D code picks up a lot more stuff than the 1D code, so there's a natural ranking here. It's the same system, it's the same physics going behind it, except the dimensionality of the issue. Now, we're supposed to have a 3D code operational, but we don't know how many we'll get in a year, how many runs, and I think we'll probably get in the order of 30, and so there's hope. Anyway, so what we're going to do in order to do this calibration, in order to build our predictive model, is try to link the data through the ranking of the codes themselves. So what we're going to do is we're going to calibrate the 1D code to the 2D code, and then the 2D code, if there was a 3D code, to the 3D code, and the 3D code would be calibrated to the field data. Okay, so the first step here is the first thing we have is the y1, that's the 1D code, and there are three inputs. There's the vector x, there's the calibration parameter that t1 that we can dial at this stage because it's the simulator. The true value we're going to call theta, so we're trying to keep with the same notation that's been used. And the right-hand side, that's the code itself. So, and TF, that's going to represent the value for the field, the calibration parameter that appears in all the data, and all of the both simulators and of course in the field. Well, we have to run it at some value when we run the simulator, so those values will be TF, and the true value, or best value, we'll call theta. So T is the thing we stuck in the code. Theta is the optimized value. Now, so what we're going to do is we're going to write the 2D code as the 1D code, but notice we've got a theta where we had T1, because what we're trying to do is make the 1D code look as much like the 2D code as possible. And but there are two things, there's a variety of reasons why the 1D code won't give you the exact same breakout time as the 2D code. One is because, well, that theta isn't in the 2D code. You don't know what it is. So, and you're varying T1 from run to run of the 1D code. So that's one of the reasons. And also, there's some physics you're missing. And that delta there is the discrepancy that Tony was talking about the other day. But notice what appears in that discrepancy. It's the things that you can dial, the knobs that you can dial in the 2D code. It's the x's, if you will, the inputs, but also T2. You don't know what the value is for the calibration parameters that is appearing only in the 2D code, and you don't know the values of the calibration parameters, the true value for the calibration parameters, the one that is in all the data, which we call TF. It's in all the sources of information. So we can continue in this way, and we'll do the exact same thing. So what we're going to do is then calibrate the field data to the 2D code, and so we have to include another discrepancy. So if you look at the middle there, I'm going to write the 2D code, the field data as the 2D code, a calibrated version of it, plus a discrepancy, okay? Now notice the only thing appearing in that discrepancy are the things that I can change in the field, which are the x's, plus, of course, replication error, and that's your epsilon. And then we can unravel that and then write the 2D code as the 1D code, and that's what you get on the far left-hand side of the bottoms, okay? And we get a calibrated version of that. So that's the basic setup that we have. And so this builds the hierarchy and allows you to link one through the other, okay? So the spirit here is, there's really two papers by Kennedy and O'Hagan. There's one where they looked at multiple fidelity codes, and there's another paper, which is the paper on calibration. And this is kind of bringing both of those ideas together, where when they did the multiple fidelity codes, they linked the lower fidelity model to the next highest fidelity model using a discrepancy. And this kind of brings in that idea, but also with the calibration idea at the same time. All right, so what's actually happening? How would you view this? Well, one of the ways to view this as, well, they all share a particular signal. So this is the part that's all shared between the 1D code and everything else, the 2D code and so on. And the 2D code also shares a signal with reality, right? And that's the 2D code, if you will, or the discrepancy adjusted to 1D code. That's another way of viewing it. But that's the signal that the 2D code shares with the physical system, but you're still missing something, which might be, or you may be still missing something, which is the discrepancy there, and of course replication error. So that's the big idea here. So some comments about what to decide, what's a calibration parameter at each level and what's not. You just have to think about what knobs you're allowed to dial. So in the 2D code, I'm still able to adjust T2 and TF, and so those things aren't calibration parameters there. They can be treated as x's, and that's why they appear in the discrepancy. I will say that the calibration parameters here, there's a bit of and the last 2 points kind of go together, that the calibration parameters, you're not really calibrating. What we're really doing is making the 1D code looking like look like the 2D code. If there was a 3D code, we'd be making the 2D code look like the 3D, and so on. So the interpretation of the laser energy scale factor in this case is not tuning it to reality, it's tuning it to the 2D code. It's trying to say, well, how much should we downplay the laser energy in order to make it look like the 2D code, right? And in addition, you're almost certain to get important discrepancies here. So if you compare the 1D code and the 2D code, how could you get no discrepancy? How could delta 1 be completely zero, right? And that would only happen if the physics were identical, okay? And in fact, T2 and TF, so T2, which would be the calibration parameter that only appeared in the 2D code, well, it would actually have to have no impact at all. And the TF, which is your calibration parameter for that appeared in all the codes, well, that would only have to, the only way it could impact the signal would have to be through the 1D code. That would be a remarkable alignment of the stars. So I think that you're almost guaranteed in this case to have discrepancy. Okay, so you're not going to be able to remove that, I think, in this particular setup. Okay, so what's the crank we're going to turn? We're going to do the Gaussian process thing. So we're going to put Gaussian process models on all of this stuff, and run well and do our best to estimate it. We're going to use a product power correlation. We're going to use a Gaussian correlation here. That probably is way too complex a potential. It admits a lot more complex interaction than we probably need, but it was the way we set it up. And you know, you can stack the likelihood here, so you can create covariance matrices for each of the individual processes. And if you notice, if you go from right to left, on the right, the epsilon process, the error process, is only operating on the data, and so is delta 2. Delta 1 is operating on the data and the 2D code, and so on. And eta 1 is operating on all of them, all of the sources of information. We set up priors here. I'm just going to throw some stuff out. I'm going to run out of time, so I'm not going to talk too much about these, but you can set this up. And actually, we used as an engine for this the Los Alamos code, the GPMSA code, and so Jocelyn Go is now an expert on that. So you better keep updating it, Dave, because otherwise Jocelyn's got no job skills. Anyway, so we did this is just a toy example here where we have we start off with at the top with the 1D code, and the 2D code, which is going to be the 1D code, but it's got we've got T1. So we're able to adjust T1 in the 1D code, but in the 2D code it doesn't actually appear. So we're going to stick in but there is a best or true value, if you will. And then at the far right, there is a discrepancy. That stuff does not, the TF times x to the T2 does not appear in the 1D code. And we did something similar for the, as you move to reality. So you add a little bit more discrepancy. There are thetas where in places of the T's, and there's an epsilon. So we just add a little bit of noise. So this is just for an illustration. Okay, so what do? We did 20 runs for the 1D code, 5 for the 2D code, and three field experiments. So this is a complete toy and illustrated example. And in fact, everything's nice and smooth here. So these are the 3 functions that you get. So the 1D, the lower fidelity simulator is the 1D code, and the higher fidelity is the blue in between, and the field, the signal in the field is the red curve at the top. I don't know if you can see the colors, but from top to bottom, you go from lower fidelity to high fidelity in this picture. Okay, and we chose values for the thetas. So what I have here are, I'm going to skip this and just go right to the punchline. So what ends up happening if I want to do so the dashed lines are predictions. And so on the green line on the bottom, what I've got is kind of my emulator, if you will, of the 1D code. And on the 2D code, I've got kind of almost the improved version of the 2D code is what you see in the dashed lines. You actually have some intervals there. And what ends up happening in this really toy example that is super smooth is that you get this dashed line at the top going through the red, because that's the red curve at the top is what you're really after, and you're doing a pretty good job of prediction. So, but we didn't expect to do poorly. But what I did not want to do, you want to discover if you can't do a simple problem, you can't do any problem, and this seems to be doing the right thing. All right, so let me just get to the punchline for the crash in this setup. What I've got on the left, so let's take a look at the top left plot here, and what I've got are all the runs in the 1D code just plotted there, regardless of their input value. They're just all there. Just gives you an idea of the span of the output for the breakout time for the shock. On the next green band is all of the 2D code runs, and then we had 8 field experiments. And so what this is so the dot, if you will, the circle is that field experiment. And this is a leave one out study, so that particular observation is left out, and what we're going to do is fit the model and predict that value. So the first line there is the 1D calibrated simulator, if you will, is the 95% prediction interval, or it's a posterior interval for that particular shock breakout time. The one beside that is the calibrated the 2D one, and thing at on the far right is the whole thing, the whole 90. That's the actual prediction interval that we have, and we've done this for each of the 8. Leave one out, so we have 8 plots, and so we did that for each one of these. And what you're supposed to see here is that things are going okay. But I'm going to give you a bit of a note of caution. So this seems to, but there was a lot of, we didn't just do this and say, wow, it worked. It's like there's a lot of coding that goes into this, and everything failed before that. So as an example, one of the things that we got, this was one of the first plots that Jocelyn showed me, and I thought, wow, this is great. Now, the one thing we do know is that the experimental uncertainty is about 1 times, the actual apparatus, the best you can possibly hope for, is about 1 times 10 to the minus 10. All right, so this is almost godlike, because it's doing better than the machines, right? And you're like, wow, what's happening here? And so this is something I alluded to the other day, was what really was happening is that the discrepancies were sucking up the experimental variability. We don't have a lot of data. We've only got 8 points, and it was taking part of that epsilon and interpolating that noise, right? And so the choice of priors here turned out to be really important, because what we did was we fixed the mean of the inverted gamma to be roughly, actually we put a particular lower quantile to be roughly what the known experimental error for the machines, and then fixed the 95%, the 95th percentile for that same distribution, so that would give us a tail that we were happy with as well, so that it would kind of wiggle around in an area that it would be able to be larger than the experimental error, but certainly really unlikely to be smaller than the experimental error of the apparatus, the measurement system. And that's something to be careful with in these. It certainly was in this problem. And so we were really happy for a while, because we were doing better than reality. So we didn't even need reality anymore. But it's just not the case. So I'm going to skip the calibration thing, so I'm out of time, the posteriors. Now, I will say one thing about design. Since this was a design, there was a lot of talks on design. There's a lot of the theme is that we have the ability to add experiments, do more computer runs, and we've been doing it basically trying to improve the predictor. And so it's been through integrated mean squared error, and we're going to be able to do this. And in principle, we were able to inform which field trials would actually be the ones to run. I don't think we'll ever be able to inform to get them to run the field trials that we want them to run, though, because there's physics that actually they'll say, well, we have 10 to 12 runs per year. We'll probably get 8 to 10 observations, and here are the 15 physics situations we're going to explore. You can inform us on the rest. And if you do the math there, we're in negative territory. So that's fine. But the methodology is there. And one thing I will say that we did find was that one field data point is worth a whole lot more than a lot more simulations. And you got hundreds of simulations, and you still can't get, the value of one field observation. So at least you're able to. But playing this game with the IMSE, you're able to kind of weigh your options and balance between, do I want a 1D run, a 2D run, a field trial, and at least say what are we likely able to do. So I think I'm going to stop there. So thank you.
You have time for maybe one question?
Oh, the pity question.
Pardon?
The pity question.
Where'd you get that shirt?
It was a pajama shirt. What can I do?
My question is sort of similar in spirit to the question you asked me in terms of what if the high fidelity and the low fidelity, it's not to your advantage to use the information in low fidelity to be able to use the high fidelity for inference.
Okay, so this is a really good question. So when you look at that movie, unfortunately I didn't show the whole movie, but it's got all these other features. So clearly the 2D code is better in some sense at capturing the features of the shock than the 3D code. But when we're looking at these one-dimensional features, actually, the thing that is, so what we did was we did this study, we did the whole Kennedy-Nohagen thing just on the 1D code. And we did the whole Kennedy-Nohagen thing on just the 2D code. And then did this combined thing. And when we look at on constructed examples, we always do better. For this data, the 1D code with the usual Kennedy-Nohagen thing, ignoring the 2D code, actually gives better results. And there's a reason for that, is that it is clear that the majority of the features are picked up by that 2D code. However, for that one-dimensional feature of breakout time, it's not necessarily better. So despite the fact that you've got something that's higher fidelity and picks up a lot more features, gets all those eddies and things like that, that's true. But what about just the breakout time, which is something that may be much easier to model than all the features of the shot? And it turns out the lower fidelity model, we had 1,000 runs compared to 100 for the 2D, but that lower fidelity model seems to do at least as good a job in this extra effort in this particular case.
So in this case, it's never clear actually when you have this delta what the thetas are estimating. You talk about as a true thing, but because of the fact that there is a discrepancy, what Mother Nature may say be using may be quite different than is needed to make the sum equal to the mean of the true response. So did you have any issues with the posteriors of these thetas running into boundaries, or and how did this affect the estimation of the sum of the two?
So the answer is no. We did not have, in this particular case, we did not have a problem with so we've had this problem before with just the regular Kenny or Hagen thing as well, where the thetas would be pushing up towards the boundary. That did not happen here. They were sitting pleasantly in the middle of the range.
Where you guessed the range was going to be or something.
Yeah. So but it wasn't all bumping up, and we also didn't get the bimodal or trimodal distributions that often kind of appear in these cases where you get discrepancies trading off of the things.
Right,
That didn't
right.
happen in this case.
Okay.
We were expecting it though.
Let's thank the speaker again.